Hello everyone and welcome back to the channel. Today I will be talking about circular task queues in C. Now I know it's been a while since I've uploaded a video, but I'm getting back into the routine of making new content for you guys every single week, so stay excited for that. Now in a previous video I've talked about a circular queue. A circular queue is a first in first out data structure like a regular queue, but the big difference is we are able to wrap the front and rear pointers around the queue so we don't waste any space and we can utilize the whole array that we've allocated for it. So a regular queue might look like this. So we increment, if we want enqueue an element, so push onto the queue, we're going to increment the rear pointer, and if we want to pop from the queue or like dequeue from the queue, we are going to increment the front pointer. Now let's say that instead of storing numbers in here, I've got some function pointers stored in this array, and these function pointers operate on some data and perform some action. The specifics of this function is not important. All we know is that this queue holds function pointers which run some tasks. Now, a common thing that we might have is for some thread on our computer to be going through all of the queues inside, to go through the different functions inside of this circular queue and execute them, right? It's a common thing we want to do. You might want to push a bunch of stuff that we want the computer to do onto a circular queue and just make it pick out things one by one and execute all of them. So it's a task queue of sorts. We have a bunch of tasks in the queue and the thread just goes through and executes all of them. So let's say I've got a thread right here and it's activated. What it's going to do is going to go to the front pointer because that's where we dequeue elements from. So it's going to go to the front pointer, it's going to retrieve the function f6, the function pointer, and then it's going to execute it, right? Once we've executed that, we can just dequeue the element, so increment the front pointer, and now we're at f7. So if you want to run the code at f7, you dequeue again, so just run the code at f7, then increment the front pointer once again. And then if you want to add new functions or tasks onto this queue, we can just increment the rear pointer and enqueue from there. So it's pretty simple stuff. Now let's say I have a thread pool. Okay, so a thread pool is just going to be an array containing a bunch of threads. So let's say I've added 4 more threads in here, so in total I've got 5 threads. I'm just going to rename them thread 1, thread 2, thread 3, thread 4, thread 5, etc. A thread pool will solve a problem that we had with the previous strategy. So before we only had one queue, so we only had one thread, and that will go to each of the tasks in the queue individually. Now if you have a very large queue with lots of tasks in there, that sounds quite inefficient because you have to go through each one by one, when theoretically if we had multiple threads we could execute them in parallel, right? So this is where a thread pool comes in. The thread pool is just an array of threads, and we're going to have to make the circular queue thread safe so that multiple threads can then run tasks inside of the queue. So let me show you guys how that would look like. So let's say I've added some more elements onto the queue, so F3, F4, F5, F6, so more functions or like tasks as you can say, and then I'm going to move the rear pointer over to the front of the queue. Now let's say all the threads inside of this queue are waiting on a semaphore. Now a semaphore is a signaling object. So if you guys aren't familiar with multi-threading, this is a basic introduction to how it works. So if you have multiple threads and you want to make all of them wait for a specific signal, or wait for us to give them a signal before they do something, we can use a semaphore. So all of these threads are waiting on a semaphore and they're all in a sleeping state, so I made all these boxes red to signify that. Now let's say we run a dequeue operation, right? So I run dequeue. So dequeue is going to go to the front pointer, execute the task on it, then increment, right? Or we can just say it's gonna make a thread do that. So when we run the dequeue function, it's going to increment the semaphore count. So currently the semaphore count is 0, and when the semaphore count is 0, all the threads are asleep. When we increment it, a random thread from the queue will wake up. So let's say it's thread 4 this time. It will wake up and then it will decrement the semaphore back to 0. So this could be thread 1, thread 2, thread 3, thread 4, thread 5. It could be any thread. So some random thread, whichever one manages to receive the update first, will wake up and decrement the semaphore. So now thread 4 is active. It's going to then look at the circular queue, and then it's going to go to where the front pointer currently is, execute function 1, and then it's going to increment the front pointer. And then once we finish to run the function and we increment the front pointer, thread 4 is going to go back to sleeping state, and now the semaphore counts back to 0. So let's say run DQ again, and this time thread 5 wakes up, right? It could be any other thread, but this it just happens to be thread 5. Thread 5 looks at the front pointer, executes the function f2, or a function f with a parameter 2 passed into it. Then the front pointer is incremented. So as I was editing the video, I realized I explained this a little bit wrong. We increment the semaphore whenever we enqueue onto the queue, so whenever we add a new task, because we want to signal to the thread pool that there's a new task which needs to be done. And whenever a thread wakes up, it will just dequeue from the queue, so get the first element in the queue and then execute that. So that's basically how it works. So we don't increment the semaphore on dequeue, we increment the semaphore on the enqueue. And now I'm just going to go through a practical example of this and write a working circular queue in C. Okay, so now I'm going to explain how we can write a thread-safe circular task queue in C. So I just got back the code from a old tutorial about circular task queues, just queues in C. I'll put a link in the description to that video. And inside of that we had this simple circular task queue written down, right? Now the first thing that I want to do is just create a thread and then just make it print out something, right? So what I'm going to do is I'm just gonna get all this code right here. Actually, I'm just gonna delete all of it, and I'm gonna rename this queue actually just to circular queue, right? So let's say I want to create a thread. I'm on Windows right now, so if you're on Linux or any Unix-based operating system like macOS as well, you're going to have to use pthreads, which should have similar functions for the operations I'm going to show you. So if you want to create a thread, I'm just going to say thread is equal to create thread, and if I just open up the documentation right here, create thread has the following arguments. So I'm just going to copy this, then I'll explain all of them. So the security attributes, I can set that to no. I'm going to set this to 0, which is the stack size. So I can specify a custom stack size for this thread. If you put it to 0, I think it defaults to it gives a default value, which I think is 1 megabyte. The start address is going to be the function which the thread's going to run. So I'm just going to say, what should we say? Keyword win API. And then it's going to be, let's call it thread func, taking a void pointer of parameters, and let's just say for now it's going to print out hello world from the thread. Okay, then return 0. So I'm just going to set that to be thread func parameters. So this parameters void pointer right here, this is the data we can send to the thread. So I'm just going to set this to be null for now, right? Creation flags, we can just set that to be null as well, I think. And then actually I'll set it to be 0. Then what's this last one? The thread ID, I'm going to set that to be null. So we can specify a custom thread ID, or we can just set null. It's going to not return anything for us. So let's just organize this like that. Okay, so we just created a thread, and theoretically if we just run the code right now, keyword win API. Oh, okay, I think I know what happened. We forgot to include windows.h. We've got to include that to use these functions. Okay, so you run the code, we don't get any output. Why don't we get any output? Because what happens is Windows creates the thread, and before it gets to running any of this code, we just terminate the main program. And when we terminate the main program, all the threads associated with this process will also be destroyed automatically as part of the cleanup. So what we want to do is to wait for all the threads to finish running their functions and then terminate the program. So how can we do that? Well, there's a very useful function Windows has. It's called wait for multiple objects. Now we can also have, I think, wait for single object as well. So if you want to just wait for a single thread, right? I'm gonna use wait for multiple objects because after I show you guys this initial setup, we're gonna turn this single thread into a array of threads, so a thread pool. So it just makes more sense just to use this for now. So we're gonna pass in the number. I think I can get documentation. Yeah, we got documentation for this. Okay, this is great. So first parameter is going to be the number of threads in this array. So right now it's just one. Second is going to be a handle, so a pointer to this array, and it's going to be the amount of time we want to wait. And actually, no, this is not the amount of time we want to wait. This is, do you want to wait for all of the threads to finish? It was like selective ones, I believe. And then the last one is how long you want to wait for these threads, right? So I'm going to first pass in one thread, right? Just a pointer to the thread because one element, so one element array. I'm going to pass in true for, I'm not fully sure what this parameter does again. Let me just quickly read it. Documentation isn't pulling up. Yeah, I think it's just you want to wait for this. You want to wait for all the elements in the array, and then infinite is going to be the time. So infinite is just like wait however long these threads take to finish running their functions. If they never terminate, that's fine. Just continue running it. We can close the program manually. And if whenever they finish, just return and continue on. Just finish running this function, then continue on to return 0. So this is a blocking function. As long as this function is running, the main function will not get off this line. So it's going to wait until all of the threads. So right now, when we've got one thread, is finished running this function, and once they finish running it, we're going to return 0. Right. So if I now run the program, we get hello world from the thread. I'll make the font a bit bigger. Yeah, there we go. So hello world from the thread. Now the next thing that we can do is we'll turn this into make a bunch of threads, right? So let's say I want to create a thread array. Actually, before I make a thread array, I'm gonna pass some data into this thread. So what I'm gonna do is create a struct, and I'm gonna call it thread params, right? It's gonna have an ID, let's say, for the threads. We can also pass in, let's just say, some sort of string they want to print out for now. So I'm just gonna create and then string is equal to hello world. So let's say thread params pointer thread params is equal to, let's pass this pointer to a thread param pointer. Thread params string thread params ID. Okay. Yep, so let's just do that. Then we have to pass this params object when we are creating the thread. So let me pass that right here instead of null. Thread params undeclared identifier. Oh yeah, it's for this right here. So yeah, now we're just printing out thread 1. So we just passed all of this thread params struct into this thread right here. Okay, so that seems to be great. Now the thing that we have to do is just create a pool of these threads, right? So create a massive array of these threads. So I'm going to do it is, well, let's create a for loop. So say for int I is equal to I is less than max threads, I plus plus. going to define max threads really quickly. So queue max size, let's say max threads equals I don't know, 20. Actually no, 20 is a bit too much. Let's say, yeah, let's say 10 for now. 10 seems like a good number. So 10. Then we want to create, actually have to create 2 arrays. So want to store the parameters. So thread params array is equal to that, and then the actual thread array equal to that. So say thread params array equals thread params id is equal to I, and let's say string is equal to hello world again, just as an example. Then we just create the actual thread. So you say thread array at I is equal to create. Just gonna steal this function really quickly, and I'm just gonna put this right here. So no. So thread func and say thread params array that's I. I'm going to do that. So yeah, that's pretty much it. And then wait for multiple objects, say max threads, and then just pass in this array right here. So say thread array. Okay, let's fix some of those errors. You have to tell it how big the arrays are going to be. 73, that should be a comma. Const handle different level and direction from handles 10. Oh yeah, I don't need to pass and point it there. Okay, so there we go. So all 0, 2, 9, 4, 3, 6, 7, 1. Yes, so these are basically Windows spins these, so these strings will print out things in different order. But as you can see, we've got 1, 2, 3, 4, can't see 5, 6, 7, 8, 9, and 0. So like it's 10 threads, but the indexes start from 0, so 0 to 9. So there we go. We got all 10 threads being spun up, right? Now, how can we make this? How can we basically add tasks onto this queue and then run those tasks, right? So how do we create this? How do we use this circular queue we have right here to create a task queue? So let's just say that we already are passing stuff into this circular queue. So the thing you have to do is make a semaphore, which is going to wait on, which is going to be incremented whenever we call the enqueue function right up here. So if you guys aren't familiar with what a semaphore is right here. So you see a semaphore object synchronization, blah blah blah. The things that we care about are these two functions. We have create and then we have release. So create semaphore A will create a semaphore for us, and then release semaphore will then increment the semaphore count. And I'll show you guys what that means in just a minute. So if I just do, first create the semaphore, I say handle, because it will return handles, at least in Windows. Create semaphore A. What does it need? Let's see, number 1. So it needs security attributes. That's going to be null. It's going to need an initial count. I'm going to set that to be 0. A maximum count, which, let's see, if I must be greater than 0. So I'm just going to say queue max size, because we can't really have more tasks than that. And then what's the last element? Name object. Oh, this can just be set to null. So let's set that to null. Right. So let's see if that works. Okay, that's great, it works. Now, the thing that we have to do is pass this semaphore into the function. So let's say handle semaphore them pass that in as well. Okay. So you might be wondering, okay, what's the semaphore thing? How does it actually work? So the idea behind a semaphore is very simple. So we have certain threads which are waiting on the semaphore. So we can use the function wait for single object. I mentioned that before. So if you look at the parameters, when you pass in the handle and the duration, so say thread params semaphore infinite duration. So just wait until I call releases. I'll show you what it does in just a minute. So we have this thing right here. Now I want you guys to think what's going to happen when I run this code. So what do you think the output's going to be? So just keep that in your mind. So if I compile this and you run it, currently nothing's happening, right? Which is a bit weird. So why is nothing happening? Because we created the threads, right? Then we have this code right here to print out the thread ID, the string. So what happens is the semaphore's count is set to 0, right? So when we create the semaphore, the second parameter right here is the initial count. It's set to 0. This function right here is the blocking function. What that means is that until this function finishes running, it won't run any code. So the threads are just stuck here. That's why it keeps on running. And this function will only terminate, or wait for single object to only finish, once the semaphore's count is greater than 0. So let's say 1, 2, 3, 4 up to the queue max size, which is 10. So like as long as if it's greater than 0 and it's able to decrement it, then it will finish running this function and continue. Then it will basically terminate this function and continue running the rest of the code. So what that basically means is as long as the semaphore's count is 0, all the threads are stuck. Now what if I wanted to, let's say, how can I increment this counter inside the semaphore? So I can say release semaphore. So this function right here is release semaphore. So I say the semaphore, the release count, and the previous count. So release count is how much you want to increase the value, and this is a pointer if you want to receive the original. I don't care about the original. So I say release semaphore. I'm going to pass in the semaphore object. I'm going to increment it by 1, and I'm going to pass in null because I don't care about the original value. So if I run this again, what do you think is going to happen? Well, we've got one thread which turned on, thread ID 0, this happens to be. I said hello world, and if I run this again, we get this, but yeah, thread ID 2. So what I'm trying to show you guys is that whichever thread manages to decrement the semaphore, so all these threads, they're just waiting for the semaphore, right? They're in a sleeping state, they're not using they're using very little resources. They are all waiting for the semaphore to increment. Once the semaphore increments, one of the threads randomly will see it first, just based off which one the CPU is running currently. Whichever thread sees it first, which is random, it will, or not random, it's just like it depends whichever one the CPU is running. Once the thread sees that, it sees the incremented count, it's going to decrement it, and it's able to decrement it. This function will terminate, and then we continue running the rest of the function. So in essence, we can control we can basically make all these threads sleep until we tell them, hey, there's something in the task queue for you to do. Then one of them will randomly wake up, get to the task queue, retrieve an item, and then go execute it, and then go back to sleep. And then once we enqueue again, another thread is going to wake up, find the item in the task queue, run it, and then go back to sleep, and repeatedly. So if you push a bunch of items and increment the semaphore like 5-6 times, all those threads will wake up, and then they'll try to get something from the queue. Now what's going to happen is if you have like 5 threads trying to access the queue at the same time, there's going to be some issues, right? Because as one might be reading the data at the front pointer while the other one's incrementing it, and then we have a bunch of like weird errors with that, like race conditions. So how can we solve that? And actually, before we solve that, I need to pass the circular queue into this. Let's pass it into queue. Let's see, dot queue equals queue. Right, I already created the queue before, and actually, so I'm gonna do a pointer so we can use it inside the thread function. So the reason I'm putting pointers here is because the rest of them already are pointers, but if you want to run the peek function inside of this thread, right, we're passing a pointer in, so we have to make sure we can pass a pointer right here. We can dereference it, that's another option. But okay, so we passed the queue in, and we have a way for these objects to wait. We have a way to control when the threads are asleep and awake using the release semaphore function right down here. Now there's one more thing that we have to do, and that is prevent race conditions. So if you guys aren't familiar with what a race condition is, it's not a simple concept, but when you have multiple threads trying to access the same piece of data in memory, what can happen is, let's say we have thread 1 and thread 2. Thread 2, we both tell them, let's say we tell thread 1 to read data from this, let's say pointer A. So I'm gonna start doing my hands in the air. I'm gonna say this. So thread 1, then we have thread 2. Right? Let's say we have this data right here called A. It's just like some, let's say 10 byte array in memory, I don't know. So let's say we tell thread 1 to read from it, and we tell thread 2 to write some data, and you tell them both at the same time. What can happen is, as thread 2 is writing to the data at A, thread 1 might try reading from it, or like vice versa. Thread 1's reading from it as thread 2's writing from it, same thing. What happens is that thread 1 will probably get invalid information because thread 2 is actively changing the data as thread 1's reading it, so we get incorrect data, and this is a race condition. We can also have conditions where both threads are trying to write to the data and they're overwriting each other in weird ways, and the data ends up being corrupted. So how can we solve this problem of having data being corrupted or misread? So there are 3 solutions which we can use. So one is just using a mutex, the second using a critical section, and the third is finding a lock-free approach. Right, so these are 3 different strategies. A mutex is a object, actually I'll show you guys right here, I've got the documentation for it. So mutex synchronization object, blah blah blah. The whole idea is, let's say I've got this code right here, right? I can say like acquire some mutex, right? I can say release mutex. Let's do it here as well. So the idea is basically this: when a thread acquires a mutex, if you have like 5 different threads, right, and all trying to access some piece of data, what we can do is have a mutex there. So this mutex basically says is, whenever one thread acquires a mutex, no other thread can acquire the mutex. They're all just waiting for it. So let's say I have thread 1, 2, 3, 4, 5, and I basically tell they all try to access some piece of data. What's going to happen is but in order to access that piece of data, they have to acquire the mutex. Thread 1's going to acquire the mutex first, let's say. Then all the rest of the threads are just waiting because they can't do anything until they acquire that mutex. So thread 1 can run whatever code it wants without having any problem or having any worry that some other thread might try to come read or write from the data they're trying to access. Then once thread 1's finished doing its job, it can call release mutex, and then whatever threads were waiting, one of them will be able to acquire it again and do the same thing. So in a sense, we have one piece of data and multiple threads trying to access it, but they can only access it one at a time. So we don't have that problem of multiple threads trying to intermix between each other, or try to access the same data. So a critical section is very similar to a mutex. So I've got this thing right here. The only difference is that a critical section is a lot more lightweight than a mutex. So a mutex can be used across threads, at least on Windows. It can be used across threads and processes. A critical section can only be used across threads, so in the same process. And because of that, it's a lot more lighter weight because it makes less system calls and a lot of other reasons. So they are basically this. They're pretty much this. They do the same thing, except mutex can be used between a thread and a process. However, a critical section can only be used across threads and within the same process. The lock-free approach is the most complicated out of these 3, and I'll explain that in this video because it's quite an in-depth discussion. But the general idea behind the lock-free approach is we use something called atomic instructions, inside of which the CPU supports, and then we try to work around having to acquire mutexes and locks. So it's theoretically, in some areas it can be a bit faster or it might be preferable, but it's a lot more complicated. I won't get into that. So we're going to use So we're going to use critical sections for this video, right? Because we don't have multiple processes and there's a lot more lighter weight than using a mutex. However, the code's pretty much the same. So if I look at a critical section right here, so we have two functions: enter critical section, leave critical section, and we're going to initialize the critical section. So I'm going to first run the initialize function. Just going to copy this, right? So let's say right here I want to create the critical section. I'm going to pass that in right here, pointer to it. That's what it requires, right? And if you're wondering how I knew it needs a pointer, it's look at the documentation right here. So whenever you have in Windows, you have LP before some kind of variable here. It basically means pass a pointer to the variable. And we actually see that if I go to LP critical section. Let's see a bit deeper. We can't go deeper, but basically it's just passing a pointer to a critical section, right? So critical section right here, we created it, we passed it in. It's initialized. I'm gonna pass this into the thread parameters. So say critical section, right? And let's see, pass that in right here as well. Critical section, right? That looks pretty good. And this is the point where we start using the queue functions, right? So enqueue and dequeue. So how we're going to do this, we want to enqueue things onto the item, and enqueue things onto the circular queue, and whenever we enqueue, that means we want to increment the semaphore, right? Because that means we've got work for the threads to do. And in the functions, the threads will call the dequeue function because they're going to pop from the end of the start of the queue, right? Because it's first in, first out, and it's going to run the code right here. So I'm going to do just wrap the whole thing in mutexes, so critical sections. So if we look right here, oops. So we've got enter critical section and leave critical section, right? So we're going to say enter critical section right here. I'm going to pass in the critical section. And I'm just going to pass it in right here. I'm also going to pass in the semaphore. I'm going to explain why in just a moment. Also need to do it right here. Okay. So you might be wondering, why did I do this? And I'll explain in just a moment why. And then whenever we do this, we're gonna increment the semaphore. So I'm gonna do this, go back here, it's right here. So whenever we have space in the cube, we'll increment the semaphore. Now you might be asking, why have I entered a critical section here? It's a bit weird, right? The reason is, if you see the dequeue operation, well, we've got the back pointer right here, but we are incrementing the occupied variable, and we're also changing it right here. So what can happen is, as we're trying to increment the occupied variable, so we're trying to enqueue things in the main thread, some other thread might be running in the background trying to do some work, and might be dequeuing and then changing it as well. So I'm putting a critical section here so we can just block that. So when the main thread tries to add something into the queue, we know that no other thread's trying to access it. So it's going to add this here. Also, what I can just do is create a bool success variable, set that to false, and then success equals true, return success. So then I can just remove that thing right there. And then for this one right here, I'm just going to pass in the critical section. That's all we need for this one, because the dequeue operation will be used by the threads in the thread pool, right? So I'm gonna once again add this stuff right here. And then I'll say, instead of returning element here, we're just gonna return it at the end. So say int element equals -1, right? And then we'll just return element. So we're just going to set that there so we can just remove the extra return statement. So that looks pretty good to me. Now the last, I'm also going to add the critical section right here. I mean, it shouldn't be a actually, I don't think we need to do it right here because we're just reading the data, but another thread might be trying to change it then. I'll add a critical section right here. I'm not sure if it's required, but it is better to be safe then. Sorry, so let's add this thing right here. Int the element equals -1. Right, element equals this, then just gonna return it right there. So if let's see, fix some of the errors. Yeah, I'm not sure what's wrong here. Can't see anything wrong. It says missing a ending parenthesis before a star. Oh, okay. Wait, semaphore. Oh, I think this is why. It's the handle. So it's gonna pass in the handle right here. So circular queue cannot be converted. Okay, so I have to pass a pointer to the queue. Okay, that's great. So now what we have to do is just, let's say, it's gonna dequeue from the queue and then print out the integer there. So let's say element is equal to dequeue from these params queue. We're also to pass in the critical section as well. Thread params critical section, and I think that's pretty much it. Let's say thread ID, and then we say integer element is equal to the element from the queue. Right, I can just take out the string. We don't need the string anymore. That's just an example. Okay, great. Let's enqueue some stuff onto the list. So I'm going to say enqueue circular queue element. Let's say 10. What else do I need? The semaphore and then the critical section. So if I did this right, it should just... No, I didn't do it. Why didn't it work? I think I have to do it after that. Okay. Still didn't work. That's a bit weird. Oh, okay, that's a bit weird. They didn't tell me about that, so we're not supposed to pass in a pointer to that. Okay, there we go. So it's printed out everything that we had there, right? So as you can see, that's basically how it works. And let me add some more elements just to show you guys. Let's say. Okay. So as you can see, that's... Why did it terminate? That should not have happened. Oh wait, that makes sense. Yeah, okay, so let me just make this into a while loop. So if you want to make it run forever, pretty much, so, like if you got continuous program, like this. So that's basically how it works. What happens is whenever the semaphore is incremented, whenever you enqueue, a random thread will be retrieved. It's gonna go to task queue, get the element or get the task, just get the integer, print it out, and whatever thread's available or wakes up first will get it. So as you can see, we get different threads pretty much every time we run it. So now it's just all 8. We get 0, 1, 1. So it's all random, but it prints out all the strings that we had before. And if we just want it, and we can run like while true, let's say if you got some sort of architecture where you have this thread pool and you have a bunch of requests coming in from some clients, and then want to continuously run the function, we can just put a while true here, so as long as the program's running, it's going to keep on printing out strings. So that's pretty much it for the video. I hope you guys enjoyed the video. Please like, comment, subscribe. If you've got any questions or ideas for future videos, please leave a comment. I'll be happy to answer to all of them. And thank you for watching. I'll see you guys later. And the code is in the description as well, in the GitHub repo. Yeah, I'll see you guys later. Bye bye.